All right. So yeah, let's get to the second talk today, also in dynamics by PjotrBuys from the University of Amsterdam. And he will talk about complex dynamics in the independence polynomial. So please, Pjotr.
Yeah, thanks. Yeah, so I will be talking about the independence polynomial, which is an object I really like because of the fact that it hits a lot of areas of mathematics and physics, statistical physics, graph theory, combinatorics, computational complexity theory, and also complex dynamics. So I will kind of focus on its connection to complex dynamics. But let's start with some physical motivation for this object. So suppose you have a piece of a very thin layer of carbon atoms that are in a hexagonal lattice like this, a piece of graphene, and you put this in a bath of, or in a room full of helium atoms. Well, what will happen is that the helium atoms, they will get in between these hexagons, but they have some repelling force such that they cannot occupy neighboring hexagons. So the helium atoms will kind of live on this dual lattice, this triangular lattice, but they cannot live on neighboring vertices. So in graph theory, we would say the helium atoms will form an independent set. And in statistical physics, the idea is that so the states will be independent sets of these graphs, but in physics, kind of any possible state, any state is possible, but different states will have different probabilities associated to them. In this particular model, the probability of a certain independent set appearing is only related to some parameter that's called the temperature and the size of the independent set. So let's do this again and go to graph theory. So I won't assume a lot about graph theory. I'll just assume that that people might know what a graph is. A graph is just a collection of vertices and edges. And an independent set is a subset of the vertices that doesn't span any edge. So for this particular this example, this graph, just a path on 3 vertices has 5 different independent sets. An empty independent set, these are the independent sets I've drawn here. And the probability of observing an independent set is proportional to lambda to the power the size of the independent set, where this lambda is called the fugacity parameter. It's related to the temperature, maybe in physics. So if the fugacity is very low, the empty independent set will have a very high probability of appearing, and if the fugacity is very high, maximal independent set or maximum independent sets will have a very high probability of appearing. So if we actually write down the probability, we have to kind of divide by the normalizing constant. This normalizing constant is just the sum over all these weights. And this is called the partition function of this hardcore model, or as I call it usually, the independence polynomial. So it's a sum over all independent sets, lambda to the power of the size of that independent set. And this is a polynomial in the parameter lambda. And if you think of it as in the context of this probabilistic model, it only makes sense to think of this of lambda as being a positive real parameter. But it turns out that for many different reasons, it actually makes sense to consider lambda as any complex parameter. And in particular, today I will talk about the complex zeros, so the roots of these polynomials, and what they can tell us, even about real parameters. So there's one result that I want to mention. It's by Li and Yang, which says that if you have some sequence of graphs converging to some lattice, for example, here, it doesn't really matter exactly what I mean by graphs converging to a lattice. You can think of this sequence of finite grid graphs converging to the infinite z-squared lattice. Well, if there is some domain in the complex plane surrounding a real parameter for which you can prove which is non-zero, where doesn't have any zeros for these independence polynomials of these finite graphs, then this pressure function, which physicists look at, this pressure function which physicists look at, well, it's always defined for real parameters, but if there is a zero-free region, Li and Yang showed that function is actually analytic. And well, what it means, so if it's not analytic at the particular parameter, this is called a phase transition in this statistical physics language. So what this theorem says that if there is a phase transition, then zeros must accumulate on this parameter of the sequence of finite graphs. All right. Another reason to look at complex zeros of these polynomials, or actually zero-free regions of these polynomials, is the following. So now I'm going to look, and this is what we're going to be looking at for the next half hour, the set of all graphs with some bounded, with some maximum degree. So let's say, so the degree of a vertex of a graph is the number of neighbors that it has, and the maximum degree of a graph is the maximum over all the degrees of the vertices. So this graph has maximum degree 5. And now we're going to look at the set of all graphs that have maximum degree delta. And it turns out that if you have some complex domain in the complex plane, that has to contain the origin as a technicality, but if you can prove that it's zero-free for all bounded degree graphs, then there is a fast algorithm for approximating the partition function within that domain. So this also says something about the real parameters within that domain, but also about the complex parameters in that domain. So this is a fast algorithm, meaning a polynomial time algorithm where in the size of the input graph and the epsilon with which you want to approximate it. And I'd like to talk about a result from ours here that proves kind of the inverse statement of this. Namely, if you look at the zero set of all graphs of all bounded degree graphs, we call that the zero locus, then actually arbitrarily near the zeros, we can find parameters for which it is actually computationally hard to approximate the partition function within the class of bounded degree graphs. And the technical term is that it's sharp-p hard, so that it's even harder than NP hard to approximate these polynomials or these values. These polynomials evaluated at that particular parameter. And and we do this via some complex dynamics. So let's see where that comes in. First, we need to have some recursion. So if you have your independent set polynomial and you take some vertex in your graph, you can kind of split this independent set polynomial up into two parts, namely summing over independent sets where the vertex is not in the independent set, and over independent sets where the vertex is in the independent set. And we kind of define these two things as for this particular vertex as z out and z in. So these are two polynomials. They sum up to the actual independence polynomial. And these z out and z in actually turn out to be independent set polynomials of smaller graphs. So if you take any independent set in G here on the left that doesn't contain a vertex, well, these independent sets correspond one-to-one with independent sets where I've just removed that vertex from the graph, right? So this particular independent set is also an independent set there, but these independent sets just correspond one-to-one. So actually the Z out is just the independent set polynomial of G where I've removed that vertex. Well, and if G was a bounded degree graph, G where I've removed that vertex is also still a bounded degree graph. So it's still in the same class. And similarly, if I look at independent sets where my vertex is in the independent set, well, what does it mean that my vertex is in the independent set? That means that all of its neighbors can't be in the independent set by definition of independent set. So what I can do is just remove V and all of its neighbors from the graph. And then we again have a one-to-one correspondence between independent sets in this graph where I've removed the whole closed neighborhood of V and the independent sets in the graph where I conditioned on the fact that I want V in my independent set. This gives me the relation that Z in can be written as the independent set polynomial of the graph G where I've removed the neighborhood of V, where I have to multiply by lambda because V is in the independent set here on the left, giving a contribution of lambda. So yeah, so we have this lemma that Z out and Z in essentially are independent set polynomials or related to independent set polynomials of smaller graphs. Yeah, and what turns out to be a very interesting thing to look at is the ratio between these things. So we define the ratio as Z in, the ratio of a rooted graph, so a graph G with a vertex V, as Z in divided by Z out. And this is a rational function of lambda. For positive real lambda, it's actually the probability that P is in an independent set divided by the probability that P is out of the independent set, if you look at this probability distribution that I described in the beginning. But in general, when we look at this, we consider this as a rational function from the Riemann sphere to the Riemann sphere. And yeah, and a big part in our proof of this computational complexity is that we look at those values of lambda where this family of rational functions does not form a normal family. So we look at these values of lambda where there is no neighborhood on which this family of rational functions forms a normal family. We call that the activity locus. And we prove that the closure of the zero locus, so the closure of all the zeros of bounded degree, the independent set polynomial of bounded degree graphs, is actually equal to the activity locus. Yeah, and I thought it would be nice to kind of go through the proof of this and see, how dynamics comes in. So one direction is kind of easy. So I kind of want to prove one direction. So if I take some lambda that has a neighborhood where on which I'm assured that the independent set polynomial is always non-zero for the class of bounded degree graphs. Well, what I claim is that this ratio can never be zero, either zero, infinity, or -1 for any graph. That's any bounded degree graph. So on this whole neighborhood U, and well, how does that work? Well, suppose it is zero, for example, well then Z in divided by Z out is zero, which means that it definitely means that Z in is zero. And that means that, well, Z where I've removed the neighborhood of V evaluated at lambda is zero. But this is also a bounded degree graph. So that's a contradiction. And similarly, for if the ratio takes on the value infinity, then definitely this numerator here or denominator here must be zero. But this denominator here, Z out, is just the independent set polynomial of a graph where I've removed the vertex V which is also a bounded degree graph, so non-zero on U by assumption. And well, -1 is technically the most tricky part. If this ratio is -1, well, either both numerator and denominator are 0, or because somehow these zeros could cancel, and you could get -1. But or you can just multiply by z out. In both cases, z in is minus z out, and zg is just the sum of z in plus z out. So it again means that zg of lambda is 0, but by assumption it's non-zero. So if we have a zero-free neighborhood, a zero-free open set somewhere for bounded degree graphs, and these ratios avoid these three values, 0, infinity, -1. And by Montel's theorem, it means that the ratios form a normal family on U. All right. So this is one direction on the proof. Other direction of the proof is kind of like, we kind of need to show something that if you have a 0, some subfamily of ratios has to behave chaotically somehow. And yeah, I will show, and I will kind of go through how we do this. First thing we kind of need is this recursion of ratios, and this is kind of a fundamental recursion that we're always considering. So if I have some sequence, or let's say just some collection of rooted graphs, I've drawn them like this. So a rooted graph again just means a graph with some particular vertex chosen as its root. And I construct a new graph where I've made a new vertex, and I've just added an edge to all these roots of these graphs. Then actually I can express the ratio as this new vertex as a rational function of the ratios of these smaller graphs, and specifically this rational function, lambda times the product over 1 divided by 1 plus the ratio of these smaller graphs. I'd like to prove this. I'd like to prove this by picture. So what do I mean? Well, what is the ratio of this newer, bigger graph? Well, it's the independent set polynomial where I sum over all independent sets, where I've stipulated here that I want this vertex in the top, and here on the bottom, I want the vertex out. So this picture kind of represents the polynomial. Well, what does it mean? I have the vertex in here. Well, that means that actually it must be out everywhere else. So I can write this as lambda times where I've stipulated that all these vertices, these rooted vertices here are out. And at the top, I can just remove V, the independent set polynomial of this graph where I stipulated V is out, where I've conditioned V out. That's just the independent set polynomial of these graphs, this disjoint union of graphs. Well, it's not hard to see that the independent set polynomial of the disjoint union of graphs is just the product of the independent set polynomials. So I can write that as the product of the independent set polynomials here. Well, on the bottom, I now just have the independent set polynomial of some graph, which I can split up as z in plus z out plus z in. And now I divide the top and the bottom by z out. And what I get is this thing where here on the top and the bottom, I actually have the ratios of these smaller graphs. So this is proved by pictures that this relation really does hold, this recursive relation to construct for ratios corresponding to these graph constructions. So what will I look at now? well, let's say I have some tree. A tree graph is just a graph that doesn't have any cycle. And what that means is that if I pick any vertex of a tree, then its neighbors, if I look at its neighbors, if I remove V, the graph splits up into its neighbors, many components, disjoint components. So, well, we've just proved that we can kind of express the ratio of such a tree by the ratios of smaller rooted trees in this way. So what happens if I look at this construction here? I have a path on n vertices, and I kind of hang a copy of each of that tree on each vertex of the path. And now I want to kind of calculate the ratio at this endpoint. I can use my formula for that. So how does this work? Well, what are the neighbors of this endpoint? Well, the neighbors of this endpoint are just these neighbors here. So those are those ratios, and the rest of the graph, which is the same graph, but then on n-1 vertices. So if I denote the ratio here by Rn, then I can kind of express Rn of lambda by this times 1 divided by 1 plus Rn minus 1 of lambda. So in other words, the ratio of this tree that I've implemented divided by 1 plus the ratio of a path of one length shorter, which if you iterate this, you can kind of see that it's just an iterated Möbius transformation, namely this Möbius transformation Fz, this with parameter mu, where it's mu divided by 1 plus z, where I've taken mu to be this parameter, this ratio of this tree. And this is why it's kind of called implementation. If I did not hang this tree on there on each vertex, the ratio here would just be this Möbius transformation iterated with parameter lambda, but I've kind of changed the parameter lambda to be the ratio of this particular tree. And this is called implementation. We're implementing a particular parameter. So this kind of motivates us to look at the dynamics of this particular Möbius transformation. So under what happens under iteration of this particular Möbius transformation. So that's not hard to figure out. And this is kind of the picture. So if you start iterating this Möbius transformation, well, if mu is a real parameter that's strictly less than -1/4, then the Möbius transformation is conjugate to a rotation. So it has two neutral fixed points, and if you start iterating this, if you iterate this Möbius transformation, it's conjugate to a rotation around these fixed points. If mu is -1/4 exactly, it has a parabolic fixed point, so it has a unique fixed point, and everything converges to that parabolic fixed point. And if mu is any other parameter in the complex plane, then there is an attracting fixed point and there is a repelling fixed point. So, and everything except for the repelling fixed point converges to this attracting fixed point. So with that knowledge in hand, let's now prove the other direction of our theorem, which says that, well, so we proved that we already proved that the activity locus is contained in the zero locus. So let's now prove the other direction. So we'll take some parameter for which we know that there is some graph of bounded degree delta that is 0 for that particular parameter. And we'll take any neighborhood around that parameter, and we'll show that the ratios do not form a normal family around this parameter. And yeah, and I'll take the degree bound to be at least 3 for technical reasons. So what is true is that there now exists, so this I will not prove, but it's true that if there is a bounded degree graph that's 0 for this particular parameter, then there's also a bounded degree tree with the same degree bound, where we can even take this vertex, this ratio vertex, this root vertex to have degree 1 inside the tree, for which the ratio is -1. We kind of saw z in plus z out. If that's 0, then, well, if z out is non-zero, then we can divide by z out, and we see that the ratio is -1. So 0 parameters almost correspond 1-to-1 with -1 parameters. There's a slight technicality that common zeros of z in and z out can cancel, but I won't focus on that. But there's a theorem that says, by White, that says there is actually a tree with a degree 1 vertex that we can implement. So what happens if we now start implementing this tree? Well, we saw it corresponds to iterating this Möbius transformation. So this is, yeah, these are ratios inside our family of ratios. So if our family of ratios were normal on this neighborhood U, then we should have a subsequence that converges to some holomorphic function. But, well, the ratio is -1 at lambda 0, but this ratio is some rational function. So the inverse of the complex plane, where I've removed the real line, everything less than or equal to -1/4, is some open subset of U, and there we saw that well, for those lambda, this iterated Möbius transformation should converge to a fixed point of this Möbius transformation with this ratio parameter implemented. But then it should do that for by analytic continuation. This is just some algebraic relation. This should do it for every lambda inside my U. But if I look at my 0, I've taken this ratio to be -1 there. This orbit of 0 is real for every n, but the fixed points of f-1 are not real. So this cannot happen, and therefore this is a contradiction, and therefore my family of ratios is not normal on U. All right. So that means that my lambda 0 is in the activity locus. So this is proving that the zeros and activity are the same thing for the class of bounded degree graphs. And this is what we kind of use. So now I'll just sketch what the rest of our argument is to show that this shows that approximating the independence polynomial is sharply hard for those parameters. Well, one thing one element of that is what's called a fast implementation algorithm. So we say that there exists a fast implementation algorithm if for any parameter that you give me and any epsilon that you give me, the algorithm returns a rooted tree in the set of bounded degree graphs that is an approximation, whose ratio is an approximation of that parameter. And we say that there is a fast algorithm if this runs in polynomial time, where the polynomial is in the size of p and epsilon. Bezikova, Galanis, Goldbar, and Stefankovic showed that if there is a fast implementation algorithm for a particular parameter, given a particular parameter, then approximating that parameter, the independence polynomial for that parameter, is sharply hard. The way they do it is kind of, if you can kind of, this fast implementation algorithm says that you can kind of create graphs which have ratios anywhere in the complex plane, and you can create those graphs. Those graphs can be small because this is a polynomial time algorithm. So that kind of means that, and you can use these graphs to implement other parameters, so parameters p inside some given graph. So essentially what it shows is that if you have a fast implementation algorithm, so if you would have a fast implementation algorithm for lambda 0 and an fast approximation algorithm, then you could kind of approximate the partition function for any parameter. Okay, this is roughly how it works. But we show that activity locus, this activity locus, anywhere near parameters in the activity locus, we can find parameters for which there exists such a fast implementation algorithm. And this kind of goes by two steps. So at first, you kind of need to show that if you're near any parameter in the activity locus, we can actually find parameters for which the ratios are dense in the complex plane. I mean, if we want to have a fast implementation algorithm, we first need to know that there exist graphs. There exist graphs that have ratios near any given parameter. But this is not so hard to show. It's kind of easy to show again that if this is not the case, then these ratios are kind of uniformly bounded near a parameter, which again would prove normality, which would contradict being near the activity locus. And then step two is, well, we pick a certain finite set of rooted trees. We picked it in a very specific way, because we know that these trees the ratios of these trees are dense, or of these graphs, we can actually take them to be trees, are dense in the complex plane. We can pick a very specific set of ratios and graphs that approximate these ratios very well. And then again, implementing these in paths. So now implementing these specific things in specific graphs in paths kind of corresponds to studying this semi-group of these Möbius transformations. And we show that we can pick them in a certain way such that using these Möbius transformations, we can build an algorithm that takes in some parameter, and we can find a sequence of Möbius transformations that sends 0 to that parameter, and it sends it there exponentially fast. Yeah. So, and the way we do it is one important aspect there is that we construct them in a way that some of them have attracting fixed points very close to the repelling fixed points of others. And we kind of play this balance of attracting and repelling them, repelling 0 to send it to any parameter in the complex plane exponentially fast. Okay. So, now that we've kind of looked at zeros. This is kind of, yeah, I've hopefully kind of motivated that zeros of the set of bounded degree graphs are interesting. I haven't really spent time yet on where are these zeros in the complex plane. So there's an important family of graphs in the bounded degree graphs, which are just this iterated set of trees where the down degree is the same everywhere and the depth is the same everywhere. So in this example, delta 3. So we look at this set of trees. Well, with that iteration lemma I showed you, you can kind of calculate the ratio at the top vertex by iterating this degree D rational map. And we have the set which we always call the cardioid. U delta is where this rational map here has an attracting fixed point. And this is kind of our main picture where we so it looks something like this. So inside this cardioid, we're looking at the complex plane. This rational map has an attracting fixed point. It intersects the real line in two parameters, which are rational functions of delta, but yeah, they're approximately minus 1 over e times delta and e divided by delta. And well, what Han, Peters, and Dec6th showed using kind of a version of studying the holomorphic motion of this this parameterized iterated family of rational maps, that zeros accumulate on this boundary. So where the attracting fixed point becomes a neutral fixed point of this rational map. What we were able to show is that zeros are actually dense everywhere outside this cardioid. Well, okay, these are all where the zeros are. It was shown in the 80s already by Shearer that the largest disk that touches this cardioid that's still contained in this cardioid is zero free for the set of bounded degree graphs. And in the same paper, Han, Peters, and Dec6th showed that there's it's intersection of this cardioid with the positive real axis. There's also an open neighborhood of that interval that is zero free for bounded degree graphs. And actually, the first question that
So in this picture, do you consider just regular trees, or you consider all trees, or like all graphs of maximal degree delta here? So this
all graphs of maximum degree delta.
Okay.
So this is a zero free for all graphs of maximum degree delta, and and here for the density we also use all graphs. Although you can actually only use trees, and that's sufficient. But that's the theorem. And and so the first question actually I worked on, which I started with my PhD 5 years ago, was is this region actually zero free for all bounded degree graphs, this whole cardioid? And I found that was not the case. There are different graph constructions, not just the D-array trees that you can construct. That have chaotic behavior, say, around different curves. And these curves intersect the interior of the cardioid. And I was able to show that means that zeros accumulate on those curves as well. So for any particular bounded degree, for example, bounded degree 3 or bounded degree 4, this is kind of more or less how good of an accurate of a picture we have of the zeros. Together with Ferenc Benz and Han Peters, we kind of investigated what happens if you let delta go to infinity. So then these regions shrink because their intersection here is only order 1 over delta. But if you then again multiply the region by delta, what does the picture look like? And here we actually can get a very accurate picture. So we can really get an accurate picture. So this outer cardioid, or let's say the whole cardioid, is the limit of that cardioid I showed before. it's actually very nice because it's the same cardioid that we saw in the previous talk, only flipped, because this is are the parameters lambda for which the map lambda e to the minus z has an attracting fixed point. And we show that the limit of the zero free region is this light blue curve. It's contained inside this cardioid. Okay, that we already knew, but we showed that it doesn't intersect the boundary of the cardioid except at the real endpoints. And we proved some things about this limiting zero free region. So let me spend a couple of minutes on how that limiting zero free region is defined. So this theorem by White essentially says for bounded degree graphs, you have this map which we already saw, and actually you can construct any ratio by just keeping applying this map. So that will construct any ratio of any graph. It's essentially another way to say it is that the ratio of any graph, there is also a tree of bounded degree delta that has that ratio. But okay, let's take that as a given. What we show is kind of we rescale lambda by lambda times delta, and this the zi by delta times zi. And the analogous set, so the infinite degree ratios turn out to be this system of sets. So where we start with 0, then we map with the map lambda e to the minus z, and then we take the convex hull. So 0 maps to lambda, and then we take the convex hull. And then we again map by lambda times e to the minus z. We map this whole line. This whole line gets mapped to this line segment there. And we take the convex hull with that line and everything we had before. So this is quite a fun a geometric dynamical system. And we prove that if you look at those parameters for which this dynamical system stays bounded, this dynamical system of taking lambda times e to the minus z and the convex hull, that those parameters for which this stays bounded is actually equal to the limit of this, the complement of the closure of the zero. So the limit of the zero free region. And this limit is in Hausdorff distance of sets. Yeah, and this allows us to prove, for example, that as we saw, the region is star convex from 0, and its boundary intersects the cardioid, the infinite degree cardioid, only in the -1 divided by e and in e. Yeah, so this is again the picture, star convex from 0, and it doesn't intersect the boundary except in the real parameters. One question that I still find very interesting about this, well, we can kind of prove that the start of the boundary here is some analytic curve, but then we kind of lose our understanding of the boundary. What we think is that the boundary of this blue set is a piecewise analytic curve, but we don't know. That's an open question. It's definitely not analytic, that much we know. There's this strange bump in here that has to be in there, which is kind of a funny bump. But okay. Yes, okay, and one more open question that I'd like to leave with. This theory of zeros and zero locus and activity locus being equal. It's true in different settings as well. For example, in different models and different graph classes. For example, also the Ising model on bounded degree graphs. And well, but here is a setting where we look at torus graphs. So you should kind of think about this edge as being equal to that edge. And we look at the sequence of increasing torus graphs. Well, for this, we can also define the activity locus and the zero locus. And could it be that they are equal here as well? And if that's true, why? Here, there is no such easy recursion in the background, but we kind of have computer evidence that they might be equal. This is the computer picture that we drew. I should have maybe put them on top of each other, but yeah, I couldn't. I only found these two pictures. But if you draw the zeros here of some very large torus graph, and here you draw the activity locus, or well, activity locus, here I draw an approximation of the spherical derivative of this ratio of very large torus. Yeah, then there seems to be a very clear correspondence between the two, but we really don't understand why it's there. Okay, yeah, and that was it. So thank you for your attention.
Yeah, thanks a lot. So let's thank Pjotr. And let me open the discussion. Any comments or questions?
Yeah, maybe I have a question. So, like, Pjotr, what is known in general about the topology, like, I don't know, like, let's say, of the activity locus for all bounded degree graphs? So, like,
yeah, so yeah, there are some things known about it, which, let's say, so let's look at the complements. So the zero free region. I think it's known that any connected component must be simply connected. So you cannot have a zero free region with a hole of where zeros accumulate inside. But what's not known is that, yeah.
But is it expected that it's like simply connected? I mean, that there is essentially like one hole, or it's expected that
yeah, so in the limit we show that it's connected, right? The zero free region, so the complement has one hole. In any finite degree, that's not known. And actually, that's a very interesting question, because if you go back to the beginning, to our motivation, I need to flip. Yes, here our motivation. This kind of says that there is a fast approximation algorithm on the zero free region, on the component of the zero free region containing zero, and we show that it's hard to approximate on the activity locus or on the zero locus. This leaves open any component of the zero free region, any possible component of the zero free region that doesn't contain zero. We don't know if it exists. We know that in the limit it disappears, but it might exist. And then there might be some fast algorithm there that's very different from this algorithm. But yeah, that's an open problem, whether it's connected, the zero free region.
And is there like some family of graphs? I don't know, like you said that, like, I mean, you've been looking at this, I think, regular rooted tree. So, like, is there some kind of more kind of complete understanding of the zero locus for some concrete families or not? Like, I mean, like the topological structure, like, for instance, like, I don't know, like infinitely many, I mean, complementary components and so on. So.
Yeah, for the independence polynomial, I don't know. If you look, for example, for the ferromagnetic easing model, there is a very clear understanding of the zero locus of bounded degree graphs. You can exactly kind of describe it. But for an independence polynomial, I don't know of any family where there is such a description. I don't know. I know, for example, the claw-free graphs are real rooted. So there you kind of know the zero locus is actually just the negative real line for the family of claw-free graphs.
So Misha, does that answer your question?
Yeah. Thanks, Pjotr. Thanks.
Okay, so are there other comments or questions? Well, let's thank the speaker again.